You know that moment, right? You're expecting perfectly round parts meeting those super tight tolerances,
Uh-huh.
and instead they come off the grinder, well, less than perfect.
Yeah.
Maybe you're looking at some right now from your Centerless grinding up, thinking these should be spot on, but they're not measuring up.
It's incredibly frustrating. A real drain on time, waste of material,
Exactly, when you're chasing that perfection.
and that frustration, that pursuit of, well, perfect roundness. That's exactly what we're digging into today.
Good.
You shared some really great material with us,
Yeah.
basically a troubleshooting guide for these kinds of out-of-roundness issues in centerless grinding.
Yeah.
So our goal here in this deep dive is really to pull out the core reasons behind these problems. Give folks a quicker path to understanding and hopefully preventing them.
Absolutely. We've got this excellent resource packed with notes, solutions for common problems. Think of it as your streamlined guide.
Right.
We're going to break down everything from just like general out of roundness
Basic.
to those really specific geometric errors like lobing, where parts get those weird polygonal shapes.
Yeah, the triangles and pentagons.
And those annoying surface chatter marks, the
Yeah.
frustration of tapered parts, and even when you get pieces that are thicker in the middle, kind of like a barrel.
Lots to cover.
Okay, let's unpack this. Starting with the foundation. Just general out-of-roundness.
It really is the foundation.
Yeah.
You can't expect to hit those tight cylindrical tolerances if the basic shape isn't even round to start with.
Makes sense.
And what's interesting is that the material you provided, it lays out some pretty direct causes for this fundamental problem.
Right. It points to a few key culprits. First off, an improperly dressed regulating wheel.
Mm-hmm.
That regulating wheel, that's the part controlling the workpiece rotation, right? So if its surface isn't perfect.
It's going to transfer that imperfection straight to the part.
Yeah.
An uneven or, poorly shaped surface there will absolutely lead to variations in roundness.
Okay.
The resource also highlights insufficient grinding passes.
Yeah, that makes intuitive sense. Like if the starting material is way out of round.
Exactly. You need enough passes to gradually bring it into that circular form. It's like trying to sculpt something intricate with just one or two rough cuts.
Or like trying to sand a really rough piece of wood smooth with just one quick swipe.
Perfect analogy. Not going to happen.
So what else? The source also flags a dull or glazed grinding wheel.
Right.
I can picture that the wheel isn't really cutting effectively anymore. It's almost just rubbing.
That's a great way to put it. It's lost its sharp, abrasive edges. So instead of shearing material cleanly, it might deform the workpiece slightly or create inconsistent forces.
Which leads to out-of-roundness.
Precisely. And the final key factor in this general overview is being too aggressive with material removal.
Like taking cuts that are too heavy or using traverse speeds that are just too fast.
Exactly. If you're trying to remove too much too quickly, the whole process just becomes less controlled.
Yeah, you're forcing it rather than like gently shaping it.
You got it.
So addressing these fundamentals, the reg wheel condition, enough passes, a sharp grinding wheel, controlling the removal rate, that's step one.
Crucial first step, yeah, before you even get into the more complex stuff.
Okay, so let's dive into some of that trickier stuff now, like lobing. That sounds weird.
Lobing is where the subtleties really start to show up.
Yeah.
You might look at a part, think it looks okay.
Reasonably round?
Yeah, but then you measure it carefully or try to fit it with something else precise, and you find it's subtly off.
Like the source says, almost triangular or pentagonal instead of truly circular.
Exactly. And that kind of geometric error, well, it just ruins any chance of a precise fit. It's a real problem.
Sounds like a major headache if you need tight tolerances. So what's behind these unexpected polygon shapes?
The source points mainly to setup problems. Specifically, it focuses on the workpiece center height relative to the wheels.
Okay.
Excessive axial thrust, especially in in-feed grinding, and any imbalance in the grinding wheel itself.
Let's start with that center height. Sounds critical.
It seems to be a huge factor, according to this material. That geometric relationship, the workpiece center line versus the wheel center lines.
Yeah.
It's absolutely critical for getting that consistent rounding action.
And the source gets specific, right? It says if the workpiece center is too high.
Yeah, too high often leads to those odd-numbered lobes, 3, 5, sometimes even 7 distinct high points.
Huh. That's a very specific link. Too high equals odd lobes. Is there a reason why?
Well, think about the contact dynamics, the forces during grinding. A higher center seems to sort of exaggerate the cutting action into these uneven periodic removals.
Okay.
The way the forces distribute, how the part interacts with the wheels, it creates these cyclical bumps instead of a smooth circle.
Right.
And the force also wisely points out, while lowering the center often helps fix this.
You can go too low.
Exactly. You can actually go too low and cause other problems. It's a really delicate balancing act, finding that sweet spot.
So not just lower is better, it's about hitting that precise optimal position.
Hmm.
Okay. The source also mentions minimizing excessive axial thrust, particularly for in-feed grinding. What's axial thrust again, and why is too much bad here?
So axial thrust is the force pushing the part along its axis. In in-feed grinding, you feed the part into the wheel to a set depth.
Right.
If you're pushing too hard against the end stop, that excessive force can actually stop the part from rotating smoothly and consistently against the regulating wheel.
Ah, so it kind of stutters or rotates unevenly.
Exactly. And that uneven rotation, that can lead straight to developing those lobed shapes.
Okay, that makes sense. You're forcing its movement instead of letting it rotate naturally. And the source suggests a fix, reducing the reg wheel's inclination angle.
Yeah, sometimes down to as little as like half a degree or even a quarter degree. It sounds tiny, but it has a big impact.
How so?
Well, that slight angle on the reg wheel is what makes the workpiece rotate, and in through feed, it also pushes it along axially.
Right.
By reducing that angle in an in-feed setup, you minimize that force pushing the part against the end stop without losing the necessary rotation.
Clever. Very fine adjustment.
It is. And the material also really stresses making sure the workpiece blade support is perfectly level and aligned.
The foundation needs to be solid.
Absolutely.
Yep.
If that support isn't true, the workpiece can wobble or shift, and that directly causes these kinds of geometric errors.
Makes sense. And the third factor for lobing was grinding wheel balance. We mentioned that for general roundness, too.
Yeah, it comes up again because it's so important. An unbalanced wheel introduces vibration through the whole system.
Right.
And those vibrations just disrupt the smooth, consistent contact you need between the wheel and the workpiece for perfect rounding. The disruptions can manifest as those lobed patterns.
Okay, so summing up for lobing, careful center height adjustment, often slightly above the wheel center line.
Meticulous adjustment, yeah.
Reducing the reg wheel tilt for infeed if needed, checking the blade support alignment.
Crucial.
And making sure that grinding wheel is well balanced.
That's the strategy.
Got it. Now let's move to another surface issue, chatter marks. Those evenly spaced ripples or waves you see.
Precisely. They're like a visible fingerprint of vibration or instability that happened during grinding.
Yeah, definitely compromises the finish.
Absolutely. Clear sign something's not quite right.
And our resource says the usual suspects are, again, wheel imbalance,
Always a big one.
incorrect part center height, seen the theme here,
Definitely a recurring player.
a dull or glazed wheel, and running the regulating wheel too fast.
Those are the main culprits for chatter, yeah.
Okay, imbalance causes vibration, we get that. How does center height cause chatter, specifically?
Here, it seems to be more about the workpiece stability. If the center height is off, often too high, like we discussed with lobing, the workpiece itself can become less stable. It might kind of bounce or vibrate slightly as it's being ground.
Like tiny vibrations.
Yeah, minute ones. But that inconsistent contact directly translates into those repeating chatter marks on the surface.
Ah, okay.
The source suggests that lowering the center height appropriately usually helps stabilize things and gets rid of that chatter.
So center height really is this delicate balance. Too high can cause lobing and chatter instability.
Seems that way, though going way too low probably brings its own set of issues too.
Right. Okay, then the dull or glazed wheel. How does that create ripples?
Well, when the wheel isn't cutting cleanly, like we said, it starts to rub or even skip across the surface.
Instead of shearing metal.
Exactly. That irregular action generates small, rapid vibrations right at the contact point.
And those vibrations get imprinted as chatter.
You got it. That's why proper dressing is so critical, as the source emphasizes. You need to expose fresh, sharp grains.
But there's a caution too, right, about overdressing.
Yeah, that's a really valuable point. If you overdress, you can make the wheel too smooth, which leads to more rubbing than cutting.
Which can also cause vibration.
Exactly. It's about finding that sweet spot for the wheel surface, sharp enough to cut, but not so smooth it glazes.
Tricky balance. Okay, and the last one. Regulating wheel speed too high. How does that fit in?
Well, if the workpiece is spinning too fast, the grinding wheel might not have enough time to properly engage and make a smooth, consistent cut.
Like it can't keep up.
Sort of. It can lead to instability right at the grinding point, and that instability shows up as chatter.
So slowing the reg wheel down a bit often helps.
Often, yeah. It allows for a more controlled, stable grinding action.
Okay, so for smooth, chatter-free surfaces, Balance the wheel, get the center height right for stability, keep the wheel sharp and properly dressed, and don't run the reg wheel too fast.
That covers the main points for chatter, yeah. Makes sense when you break it down.
Totally. Now, let's shift gears to when the part is round, but not cylindrical. Taper, one end consistently smaller than the other.
Yeah, that's another common frustration. And according to the source, taper almost always points to some kind of misalignment in the setup.
So if you see parts consistently smaller on one end, think alignment first.
That's the first place to look, definitely. Check the guides, check the wheel's trueness.
And the source highlights two key areas: the workpiece guide plates, especially for through feed, and the straightness of the dress profile on the grinding wheel. Let's start with the guides.
Okay. In through feed grinding, where the part feeds right through the grinding zone.
Continuously.
Right. The alignment of those front, the entry guide, and the rear, the exit guide, relative to the regulating wheel's axis, is absolutely critical.
They have to be perfectly parallel.
Perfectly parallel to the reg wheel axis for the part to come out truly cylindrical.
And the source gives examples, right? If the front guide angles away slightly,
The front end of the part can end up smaller.
and if the rear guide angles away,
The rear end tends to get ground smaller. Even tiny deviations from parallel can cause noticeable taper.
it's all about keeping those axes of motion and contact parallel. Any deviation messes up the geometry.
Exactly, which is why the source really stresses careful, precise adjustment of those guides, usually using dial indicators.
Not something you can just eyeball.
Definitely not accurately. And the other big factor for taper is the grinding wheel itself, specifically how straight its profile is after dressing.
Right. If the diamond dresser path isn't perfectly parallel to the reg wheel axis,
You're basically dressing a taper onto the grinding wheel.
and that shape gets transferred directly to the workpiece.
Precisely. So if you've got taper, you absolutely need to check your dressing setup, make sure that diamond path is truly parallel.
Makes sense.
And this source also reminds us, just uneven wear over time on either wheel can eventually cause taper too.
So regularly checks and redressing are key.
Essential for maintaining consistent cylindricity over the long run.
Okay, so the recipe for avoiding taper: make sure those guide plates are dead parallel, and dress the grinding wheel with a truly straight profile.
That sums it up nicely.
All right, finally, let's hit the issue of convex, or barrel-shaped parts. Thicker in the middle, thinner at the ends.
Another specific shape issue. The source material points pretty clearly to setup errors here, mainly involving those same guide plates.
Again, with the guide plates.
They're critical, and also the possibility of the grinding wheel itself having the wrong shape.
It mentions barrel shapes often happen when both guides, front and rear, are tilted towards the grinding wheel.
Yeah, you can kind of picture it, right?
Yeah.
They're pinching the pathway in the middle of the grinding zone.
Narrowing it there.
Exactly. If both guides angle inwards, the ends of the workpiece tend to get a bit more grinding pressure or dwell time against the wheel compared to the middle.
So more material comes off the ends.
Right, leading to that convex barrel shape. And the solution, as you'd guess,
Go back and make sure those guides are perfectly parallel.
meticulously parallel to the path the workpiece should take.
And the other cause: a concave grinding wheel dress.
Yeah, that also makes sense, doesn't it?
Mm-hmm.
If the wheel face itself has a hollow in the middle.
The higher edges of the wheel will grind the ends of the part more.
Exactly, creating that barrel shape. So if you see
Yeah.
convex parts, you need to inspect your wheel profile carefully and look at your dressing procedure.
Make sure you're getting a straight face, or maybe an appropriately crowned one if needed, but definitely not concave.
Absolutely. Avoid that hollow dress if you want cylindrical parts.
Wow. Okay, so from basic roundness all the way to these really specific, kind of subtle geometric errors, it really hammers home that precision centerless grinding is this delicate dance, isn't it?
It really is. A delicate interplay of getting a whole bunch of factors just right. It's rarely just one single thing.
Not just one magic bullet.
No, as the source material really shows,
Mm-hmm.
it's the total effect of paying close attention to all these interacting bits, wheel conditions, maintenance, those fine geometric adjustments in the setup.
Everything matters.
Everything matters.
So for you, the learner, hopefully this deep dive gives a really solid overview of the key things to watch out for when you're aiming for perfectly round, perfectly cylindrical parts from centerless grinding. Whether you're troubleshooting problems right now on the floor or trying to prevent them in your setup planning, keeping these ideas in mind: wheel condition, center height, guide alignment, balance, dressing, it's all going to be crucial.
Absolutely. And, considering how interconnected all these things are,
Mm-hmm.
it makes you wonder, doesn't it? Like, what seemingly small adjustment might actually have the biggest ripple effect on hitting that perfect roundness consistently?
That's a great question.
Or maybe thinking beyond just the machine, what role could the actual material properties of the workpiece play in some of these out-of-roundness issues?
Ooh, good point too. Lots to think about beyond just the mechanics. Some really insightful points there.
Yeah,
Well, we really hope this deep dive has shed some light on the intricacies of getting those perfectly round parts. If you're grappling with any of these issues yourself or have experiences or questions, we'd love to hear them.
definitely. Always learning.
It's all part of our ongoing exploration of these complex manufacturing processes. Thanks so much for joining us for this deep dive.